In this video, we'll discuss acid strength. The strength of the acid is defined by the equilibrium position of the acid's ionization reaction. Here, we see a generic example. For a strong acid, equilibrium lies far to the right. This means there is virtually 100% dissociation, or all the reactant is converted to product. In the equilibrium expression, the denominator, or concentration of the reactant, is essentially zero. There is no reactant concentration at equilibrium. Thus, the acid dissociation constant for strong acids is very large. There is also an inverse relationship with a strong acid and its conjugate base. Strong acids yield weak conjugate bases. For a weak acid, equilibrium lies far to the left. There is far less than 100% dissociation. In some cases, weak acids may only dissociate less than 5%. In the equilibrium expression, the denominator, or concentration of the reactant, is very high compared to the products, because there is mostly reactant present at equilibrium. Thus, the acid dissociation constant is very small. And weak acids yield strong conjugate bases. The weaker the acid, the stronger its conjugate base. Let's look closer at strong acids. Because 100% dissociation is expected, we can assume that the concentration of H+ at equilibrium is essentially the same as the initial concentration of the acid. This will be important later when we have to calculate pH. Now let's compare to weak acids. Because only a small degree of dissociation is expected, we can say that the concentration of HA at equilibrium is far greater than the concentration of H+ at equilibrium. Again, this is important when we calculate pHs. Here's an example of a table with some common acids listed along with their formula and Ka value. Strong acids are on the top of the table, and decreasing K value puts weaker acids at the bottom of the table. One thing that stands out is that the strong acids have Ka values that are simply listed as very large. This table shows the Ka values for the stepwise dissociation of polyprotic acids. I have included a few examples of diprotic acids and phosphoric acid, which is a triprotic acid. Notice for diprotic acids, sulfuric, carbonic, and ascorbic acids, there are two Ka values, one for each proton dissociation. Sulfuric acid is a strong acid, and its first Ka is very large. This means that one proton readily dissociates. Its second Ka is a little smaller. Carbonic and ascorbic acids are both weak acids. Notice the triprotic acid, phosphoric acid. It has three Ka values. For all polyprotic acids, each successive dissociation constant gets smaller. This means that the acid gets weaker as the proton dissociates. Therefore, the first step is generally the most important contributor to H+ concentration.